realization as to why this happened is really illustrated very nicely in this next slide. Carbon, which has 6 protons, and in this case the isotope we're looking at has 6 neutrons. The neutral carbon atom has a total of 6 electrons to match the charge coming from the 6 protons. Bohr's model of the atom says that these electrons are going to be arranged in a shell, and that the first shell has a maximum of 2 electrons, and that the second shell, the valence shell, has 4. Now, the idea of a valence shell is extremely important in chemistry. The valence shell or valence electrons are the outermost ones. And they're so important because when atoms interact with other atoms around it, that interaction involves the outermost shell. And the reason why is the inner ones, in this case carbon has 2 of them, these are called the core electrons. Those core electrons are being shielded by the outer valence electrons in the valence shell. So they are fundamentally unable to participate in a chemical reaction. So it's the valence electrons and the kind of things that valence electrons are able to do that determine what the atom itself can do. Now, if we take a look at this slide, we will notice that the hydrogen atom, which has 1 proton, the atomic number is 1, it has 1 electron going around in that first shell. If you look at carbon, the first shell contains 2 electrons, and then the second shell has 4 electrons. Now, the reason why there are 4 additional lightly labeled electrons is there's 4 more slots available to get you to 8, since the maximum number in the second shell is 8. So carbon has a total of 4 valence electrons, although the outside could in fact handle 8. Moving over to nitrogen, once again you'll see 2 electrons in the first core shell, which is always filled first, and then there are a total of 5 electrons in the outer shell, and since the maximum is 8, there are 3 open slots. And moving over to oxygen, you'll notice that once again there are 2 electrons in the core shell, and then there's a total of 6 electrons in the second shell. So if you work your way across the periodic table, you will notice that the total number of valence electrons, or outermost electrons, increases to a maximum of 8. Now, we can represent this in a simpler manner by simply using dots. So notice lithium has 1 dot. That's not the total number of electrons, rather it is the total number of electrons in the outermost or valence shell. Beryllium has 2, oxygen, as we've seen, has 6 electrons in the outermost, and finally neon has a total of 8 electrons in the outermost. Again, to stress it, the neon, the total number of electrons is 10 because there are 10 protons, but the number in the valence shell is 8. Now we can start to make sense of things. This is the periodic table. It's a bit fuzzy, but this is the periodic table, and we are showing shell by shell the total number of electrons. So take a look in the first column. You'll notice that hydrogen has 1 electron in the first shell. Lithium, which has a total of 3 electrons, 2 of them will be in the first inner core shell, and then there's 1 in the next outer shell. So lithium has 1 valence electron because that's the outer electron. Now take a look at sodium, and this is interesting. Sodium has 2 electrons on the inner core. The next shell has 8, but we still have 1 more electron to go. We need to get to 11. Therefore, sodium has one electron in the outer shell also. So hydrogen has one electron in the outer shell, lithium has one, sodium has one. Since atoms interact by bumping into each other, the chemical properties or the behavior of all the atoms in that column, hydrogen through sodium, they all have one electron in the outermost shell. So one might suspect that all of those atoms might behave chemically the same, and in fact they do. Take a look at beryllium. Beryllium has two electrons in the outermost shell. Magnesium has more electrons total, but there are again two in the outermost shell. So one would suspect that beryllium and magnesium are very similar chemically, since they have the same electron pattern in the very outside shell. Skipping over fluorine. Fluorine, F, there's going to be a total of 9 electrons because there are 9 protons. There are 2 in the first core, but that leaves 7 in the outermost one, or valence shell. Chlorine has 17 protons, or 17 electrons. 2 of them are in the first inner shell, 8 are in the second shell, but once again there are 7 in the outermost shell. So fluorine has 7 valence electrons, chlorine has 7 valence electrons. You would assume they'll behave chemically the same because they have the same number of valence electrons, and in fact they do. Finally, on the right, helium, neon, argon. All of those have all of those have a full outer shell. Helium has 2, but that's all that can fit in the first shell. Neon and argon have a maximum of 8 in each one, so once again you would assume that they would all behave the same chemically, and they do. For example, all of those do not interact chemically at all with other atoms because the outer shell is already filled. We look here at a dot approach to the valence electrons, and once again, in column 1, from helium to cesium, Cs, all have 1 valence electron. You would assume they would all be similar chemically, and they are. Beryllium to Ba, you would have 2 valence electrons, and they are similar chemically all the way across. And you can work your way and start to realize that each column has in fact the same number of valence electrons, not the same total of electrons, but the same number on the outside valence. Now, on this chart, you'll notice that there are regions that are blue, regions that are green, and regions that are yellow. The reason for that is, as we discussed in the octet rule, atoms will get rid of or gain electrons in an effort to have the outside valence shell filled, meaning it would have a maximum of 8 electrons in it. You'll notice that in blue, those atoms are going to have a tendency to want to lose their electrons and thereby gain a charge of plus. We call that grouping of atoms metals. The yellow grouping will have a tendency to gain electrons, assume a negative charge in an effort to achieve a full valence shell. Because they tend to gain, they're called the nonmetals. Now the green column or staircase down the side there, those are called the metalloids. And they're called metalloids because sometimes they will gain electrons to solve the problem. Sometimes they will lose electrons to solve the full valence shell electrons. So they sometimes have the properties of metals, and they sometimes have the properties of nonmetals. Now it's very, very important that you are able to identify that region that are metals, regions that are metalloids, and regions that are nonmetals. And you may want to mark your periodic table accordingly. This chart here is getting away from dots but trying to show you the same pattern. Notice the first column has 1 valence, the second column has 2 valence, and finally all the way over to the last column, which has full valence shells, which are either 2 for helium and then 8 for the rest. Now that organization accounts for what you see here. All that is in yellow are metals. They lose their electrons to get a full valence shell. They will assume a positive charge, and therefore they are called the metals. Over here, as discussed, these are the nonmetals, and this right here are the metalloids. They sometimes lose, they sometimes gain, depending upon the particular atoms that they're working with. This leads to a bit more specific set of groupings. You'll notice here, you might recall that all of these have 1 valence electron. They're a metal group, therefore they're going to lose that outer electron. But because it's only 1, it's given a special name called the alkali metals. This region has 2 outside electrons, and therefore this grouping is chemically very similar to each other. We call them the alkali earth metals. This group here, these are the transition metals. This group here, they're called the halogens. They will tend to gain electrons. And finally, this in purple are the noble gases. Down here we have the lanthanide series. The lanthanide series is interesting. This group belongs right actually here, but it would stretch the periodic table too wide. And so traditionally the lanthanide sequence is pulled down to this region because it makes it fit on a piece of paper better. So notice lanthanide is 57 and 58 would belong right here, which is cerium. So then you have the actinide series. You'll notice that actinide is number 89 here. And then what happens is right here should go the start of thorium, and it works its way through all the way here and then picks up again here at 104. So these are the groupings of atoms in the periodic table, and they're grouped that way because they have common chemical properties. Again, to re-emphasize that besides the alkali metals, the alkali earth metals, there's the very large grouping called metals, the very large grouping called nonmetals, and finally the metalloids, which you'll be asked to know. And that is the basic ideas behind the periodic table of the elements, developed by this fine-looking gentleman, Dmitri Mendeleev.